Thanks a lot for coming. Today's speaker is Russel Stoneback. He's from UT Dallas, and he's an assistant professor there at the Center for Space Science. He got his PhD also from UT Dallas in 2009, and he's currently working on IVM, that's the Ion Velocity Meter. He's on the instrument team for ICON, so that's the NASA Explorer mission, and also on Cosmic 2. In addition, he works a lot on CubeSats, so he kind of made the IVM smaller so that it fits on a CubeSat, and is on the NASA Sortie and NASA Sport mission. And then he also developed a CubeSat instrument to measure neutral winds. Then he is the lead developer and inventor, maybe you have heard from PySat. That's the Python Satellite Data Analysis Toolkit. This will be used for ICON and for the Cosmic 2 mission. And in addition, as graduate student, Russel worked on diffraction of waves through an aperture, developing a new long wavelength description using equivalent impedance that significantly improved upon existing diffraction solutions. And then he was also visiting India, worked more with solar physicists there, so expanding a little bit on his background. Yeah. And today he talks about EM, Helmholtz resonators, transferring power from the sun to the earth.
All right.
Thanks, Russel.
Thank you. All right, so I am very excited to be here today. So most of the things Esther just said about me, I'm actually not going to be talking about today. So I do spend most of my time on instrumentation, software, studying the ionosphere, particularly the equatorial region. So I'm giving a talk today here. I'm also giving a talk at LASP tomorrow. So the talk at LASP tomorrow, I'm going to be talking about some more of those traditional things that I work on. But when I got the official invitation to come here that I asked for, I was reminded that HAO has scientists that study the sun all the way through the Earth. So I thought it might be. I decided to take this opportunity to discuss more of my work from my graduate student days. So this is the stuff that I pretty much did to earn my PhD. So Dr. Rod Helus is the director for the Center for Space Sciences, and I did work under him. But when I started this project, I didn't know it had anything to do with space science. So I have some solutions here that I believe do apply for space science, but I approach it in a very different way. And that's because when I started this project, it really didn't have anything to do, at least I didn't think it had anything to do with the sun or the Earth. Okay, so I'm going to start a little bit with the acoustic Helmholtz resonator. So this was kind of the seed idea for my project. So the Helmholtz resonator is exemplified here with the bottle, right? It's pretty much empty. And if you blow over the tip of the bottle, right, it produces a very low note. And the wavelength of that radiated note is much bigger than the size of the bottle. So this Helmholtz resonance isn't really a wave-type resonance. It's not that there's resonant modes within the bottle, but it's an interaction between these two components that does produce a resonance. So acousticians usually describe this system with circuits, actually. So the neck of the bottle is inductive, and then the bottle itself is capacitive. So, right, you get an inductor and a capacitor together, you can get a resonance. So when you're blowing over the bottle, that's the thing that you're engaging. So of course, I wasn't particularly interested in a bottle itself. I was really interested more in a guitar. So I got a picture here of an acoustic guitar. The sound hole over here, I'm going to use my mouse. The sound hole here, a number of people think the sound from the guitar comes from the sound hole. That is not true. Most of the sound actually comes from this top plate. This sound hole here is like the opening of a bottle, right? So this is the opening, the guitar itself is the bottle, and you get an interaction between those two elements, which gives you the bass response of an acoustic. So sometimes if you see somebody playing live, they'll actually cover the sound hole up with a piece of plastic because you can get a lot of feedback live on stage. But by covering it up, you reduce that feedback, but it also changes the sound. So the project I was actually going for was not to build an acoustic instrument, but I was trying to build an equivalent instrument using the resonance of electromagnetic waves. So instead of sound waves resonating in a wood body, I was looking for electromagnetic waves to resonate in a body made of metal. And then that would radiate waves that if we recorded them and changed the frequency, it would come out as music. So both acoustic and EM waves solve the wave equation. So just the very quick summary is they both solve the wave equation. They have the same boundary conditions. They actually have the same solutions. The only major difference in terms of this music is the speed of those waves. So while an acoustic guitar, or the nominal hearing range we hear for humans, is 20 hertz to 20 kilohertz, the appropriate range for an EM guitar, if I match on wavelength, is about 20 megahertz to 20 gigahertz. Okay. So it's the same size waves, but it's a very different frequency regime. So what I wanted to do as a graduate student is I wanted to build this new type of instrument, and since I already knew the wave equation was solved, what I was really looking for was creating the electromagnetic version of this Helmholtz resonator. I wanted to come up with a solution for an aperture that was like how an acoustician describes an aperture. That way I could take the same process to actually building and exploiting a guitar. So I thought I'd talk a little bit about an electromagnetic aperture. So this is actually, diffraction is a pretty complex problem, so I'm going to take a very high-level view of it. But the original problem is listed over here on the left. So you've got like an infinite conductor, which I can't draw very well, but it extends off to the top and the bottom. But in the middle somewhere you cut a hole, right? A circular hole or anything like that. And if we have a wave that comes in on one side, and the wave is much bigger than the size of the hole, right, then it's going to diffract through here, and you're going to get a small amount of energy that's radiated through, which is very frequency dependent. So one of the classic solutions to this problem was developed by Hans Bethe, who actually, so what he did is he figured out that you can describe the diffraction of the aperture at long wavelengths using a pair of dipoles. One's an electric dipole, the other's a magnetic dipole. And the way he actually did this solution was he filled in the aperture with a perfect magnetic conductor, not an electric conductor, magnetic conductor, and then imposed magnetic currents on that conductor and said those magnetic currents have to produce fields that will satisfy the boundary conditions of the original problem, and he's able to get through. Now you may be wondering, magnetic currents don't exist. As far as we know, that they don't. There are no magnetic monopoles, but we can write Maxwell's equations with those currents in there. And then, so we know how to operate with them, and then as long as you require that the solution actually satisfies boundary conditions of the original problem, then you're okay. So the Bethe's dipoles have been very successful, but I found that they weren't exactly correct. So what he did is replace these with dipoles. What I did is I replaced this with an impedance surface. So a wave will come in and it'll impact this impedance, and based on the known, if you've got region 1, region 2, two impedances, a wave will come in and some will reflect and some will transmit based on the difference in impedance. That just comes straight from the E and M boundary equations. So I wanted to make it a little bit simpler to use the problem, so you can use it for more complicated apertures, more complicated incident fields. But then while I was doing that, I actually had to alter the description. So this is an impedance surface. So this impedance surface will first produce a dipole. But that dipole is surrounded by a conductor, so those fields will then produce an image dipole in that conductor. Now, Bethe originally did not allow any currents from one side of this metal to go to the other side, but I don't think that's correct, so I relaxed that assumption, so these image currents will then go to this other side. And these image currents will then produce an image within this impedance surface, and the image of an image is real, so then we end up with this back dipole. Okay, so in a way, it still sounds kind of like Bethe's, but because I actually am fully accounting for power as it goes through these things, it actually has some impacts here at the end. Okay, and at the end, what I get is an impedance that's equivalent to the aperture itself. Okay, so just some. No questions? Okay, so just some very brief things. This is one of the first equations we start with. This is just writing down the electromagnetic boundary conditions between two media. So the tangential component of the magnetic field has to be continuous, and the normal component of the displacement field, right, the epsilon E, that has to be continuous. Here it's written as with these fields produced by the aperture as a function of magnetic currents here. And at the end of the day, what I want to do is convert these equations into something that looks more like this, where voltage times admittance is equal to current, or equivalently, voltage is equal to the current times the impedance, right? Some things that I had to do is actually come up with a parameter over here. So you can start out, we're looking at some equivalences between an electric dipole and a magnetic dipole. I had to do some work in this area, and I came up with this constant that was very unimaginatively named B. But B turns out to be like a characteristic scale, length scale or size for the aperture. And the number I get for a circular aperture is pi a over 4. What's significant about this is that's the same effective thickness you get for an acoustic aperture radiating into a half space. So kind of early on in this project, I was finding that the electromagnetic diffraction is very similar to acoustic diffraction in ways, even though acoustic fields aren't as simple as E and M fields. Here's the end result over here is the aperture impedance. This is the impedance of a magnetic part. We've got some resistance here, and then we've got an inductance over here. It's a 1 over j omega, but it's an inverted. Yeah, it's inverted. So this is actual admittance, and then I take the inverse to get the impedance. I'm biased towards looking at things in terms of impedance rather than admittance. And then down over here, I have the impedance for the electric dipole, which is mainly capacitive, right? This is going to be inverted again. So here the S is the surface area of the aperture. B is that characteristic length scale, which depends on the shape of the aperture. For a circle, it's pi a over 4. The K is just the wave number. The Z2, this is the standard wave impedance of region 2. So you have a wave coming in on region 1, radiating into region 2. And what's really significant about this is the aperture impedance only depends on the region you're radiating into. It doesn't depend on the impedance of the region where the wave is coming from. So if you looked at Bates's dipoles, he'd have dipoles that depend on both regions, and I found that is not actually accurate. So it's only the region it radiates into that really depends on things. I thought I had included something else here. I guess I didn't make it. But this is overall kind of like the circuit. The wave is replaced by like a voltage generator, right? I've got the inductive impedance from the magnetic dipole plus the radiation resistance. I've got a capacitive impedance from the electric dipole plus the radiation resistance. Okay. So then it allows me to use kind of more standard techniques, what's called network theory, to figure out how much power is going to go into this circuit, and perhaps if I have something further on down the road, how much power would go from this circuit into those later circuits. So to check, actually, to determine if my theoretical calculations of the impedance were true, I did a bunch of modeling in ANSYS. So this is a finite element model technique. So ANSYS has been around for quite some time. It's used quite a lot in mechanical engineering, but it has a very complete set of electromagnetic tools. So over here, this is the actual model, all broken up into the finite elements. So here's where the aperture is. You can see I have a lot of elements within the aperture. So this blank space, this is my conductor. It's an infinite conductor, and it's perfect, so I don't actually need to model it, just the surface. And then you can see I have kind of a smooth, I bevel, rather than just have a straight 90-degree bend into the aperture, because you can have numerical artifacts with something that sharp. I rounded the corners off. Here is a zoom in of just what the aperture volume looks like, so you can see I really have a lot of elements within the aperture. And then if you have small meshes, you actually have to move slowly into bigger meshes. That way you don't actually lose all the accuracy that you generated with the finite mesh. And then this is kind of a larger view. So on one side I'll have a TEM waveguide, transverse electromagnetic waveguide is feeding in my waves. I've got my aperture here. Halfway through I go between region 1 and region 2, so I can change these parameters. So I could verify how the aperture impedance varies with materials. And then there's a perfectly matched layer on this side, so when the aperture radiates, when it hits this perfectly matched layer, it just kind of goes away without reflecting back. So it's a lossy layer that doesn't produce reflection. So it approximates an infinite space. And this is a picture of like the relative sizes. So this is actually a relatively high frequency or short wavelength. If I showed this to you at the long wavelengths, you wouldn't even really be able to see the aperture, because I have to size this thing based on the input waves, and everything is really big, and then I've got this tiny little aperture in there that you can't even really see. So it was a pretty challenging problem, especially I did this about 10 years ago, so computers are always getting better and things like that. So there we go. So here's some results of my impedance. So the solid curves are determined directly from the ANSYS model. I do integrations of the voltage, right? It's just this line integral of the electric field. The current is a loop integral of the magnetic field, right? And then V is equal to I times impedance. So if I have these two things, I can directly get the impedance out of the model. So that's what these solid curves are. And the dashed curves are the predictions from my circuit. So on this side, this is the real impedance. Over here, this is the imaginary impedance. Now, strictly speaking, this circuit model only applies at long wavelengths. So that's stuff like from here to the left. So it's really just this general rise. So, and it does that very well. Now, Bates's dipoles, actually, as soon as you started getting up into this area, their power would just keep going on up to infinity and beyond, right? And that was not correct. Though I do, start to diverge from the model, my impedances are doing the right kind of thing. To begin with, my real impedance actually goes down to 0. So as you go further in frequency, the higher in frequency, the radiated power from my dipoles goes to 0. So, I mean, that's a lot better than going to infinity, which we know is incorrect. And then you can see actually get the resonance fairly close, and then things, get worse. But we're in the short wavelength regime here.
Is there any difference in your model between H and B or the mu naught? Or is your mu a function?
It's just a constant. The mu would be a constant, yeah. So I changed the material properties for multiple cases. I'm only showing the cases here when I changed it for region 2. And you can see the impedance definitely changes as a function of the material properties of region 2. I also showed you the one with region 1. You just see a bunch of lines all on top of each other because it doesn't matter. So that's actually fairly significant. So the impedance is pretty good, and then I went on to actually calculate power. So one of the standing problems for aperture diffraction is something called, there are certain regions where you get superluminal behavior. So you send in a wave with a certain energy density, and the aperture is radiating, and you look at how the energy density in the aperture, and you're like, hey, that energy density is higher than the input wave. How does that happen? So I've actually come up with a solution here, which goes back to what I was talking about before with the power. So I got a little ahead of myself here, so let me back up. So first things first, this is the Poynting flux. So I went directly into the model and calculated from the E and H fields what the Poynting flux is. And here it goes up, and you can see it's superluminal here because one passed. This is 1. This is energy density of the input wave. That's about here. Things are definitely higher. So this is an effect that just comes right out of models, and it has been observed. All these other lines are aspects of my model. So transmitted power, this is what if you take just the input impedance of the wave and the aperture impedance and you put those together as the network theory, say how much power is transmitted, you get this blue curve, which at low frequencies is twice what we actually observe. But when you get up to higher frequencies, it matches. So I put these things up here because out of this full transmitted power, I had to start to divide the power based on the different mechanisms. One, you have the dipole that's radiating in front of you. Then there's power that goes into the image fields. That power then has to get transmitted to the other image fields, which then has to produce that backwards dipole, which then would radiate back. So this is kind of like the full input. From here, with a little bit of algebra, I was able to figure out how that worked. You may be wondering what this G function is. So I've taken these equations out of my paper. But so the G function, say you've got a perfect conductor right here and you've got a dipole at long wavelengths, you're going to radiate this way and you're going to radiate backwards. It'll reflect off the conductor and then go back forward. If you have very long wavelengths, the phase change is very minimal, so you effectively double your transmitted power out this way. As your wavelengths approach more of the size of your problem, that phase difference becomes more and more important. So you no longer direct all your power that way because when things add up, it's not in phase anymore. So that's what this G function calculates. You can just look it up in a book. I put it in there, I arranged things, and I figured out how things got divided. So once I started dividing how much power is going to go into my forward dipole, how much power is going to go into my backward dipole, the forward dipole is this orange curve or red. And you can see it now, it matches the actual Poynting flux very well. It also gets up here into the superluminal area, and then it goes back down. The reason why it gets superluminal is this green curve is the power and the backwards dipole. So at low frequencies, you get equal power in both, radiating forward and radiating backward. But as the wavelengths become smaller compared to the size of the problem, that dipole is aware that it's not really a real dipole, right? It's an image of an image and things like that, and there's all these distances it has to go through. And it turns out that at around 1, the direction of the power switches. Instead of radiating backwards, it now starts to radiate forward. So the extra power that's coming in is not because it's coming from nowhere, it's because it's coming from the wave that's hitting around the conductor. So it's actually kind of siphons more, funnels more power through the aperture than is just directly incident upon it. So when it goes negative, I do it dashed. So now it's increasing the forward power. It goes back to solid. It's decreasing the power a little bit. Back to dash, it goes back up. So that's kind of a nice solution there. There's a number of problems that got solved right here with my impedance description and breaking things out into impedances. And then this was not actually in my dissertation, but one of the longest standing problems in aperture diffraction is that there were solutions that worked at long wavelengths and there were solutions that worked at short wavelengths, and the two never got together. After I finished this, I was post my degree. I came up with that. It's like, hey, I got a plan. I think I know a way to actually get full diffraction solution. I was like, but it's going to take some work. And after thinking about it a little bit more, I said, yeah, that will definitely take some work, but I can take a shortcut to figure out if my general idea is going to be correct. So this is my shortcut. So down here, it's all nice and good. This is imaginary impedance. It matches up very well. Now over here, we're in the short wavelengths, and you can see my circuit description is now starting to match the model extremely well. Same with the real impedance. This little diversion down here is more of a calculation issue than it is an actual, I think, a real variation in impedance. I don't do so well in this transition region. I get a little above on the dipole resonance, but I actually expected this to happen because I had to break my solution a little bit to take this shortcut. But it definitely did, I mean, even though this is a not a full complete solution and it's just like a beta test of the full thing, I've already achieved more with my shortcut than I think any diffraction solution has before in terms of the long and short wavelengths. So there's only this short period now, this small area right in here where things aren't good, but the long wavelength and the short wavelength regime is in really, really good shape. Okay, so that's kind of some of the stuff I did as a student. I actually just started communicating with an Amélie Rabat. I hope I don't pronounce her name super incorrectly. So she's in France. She's a student right now. She's trying to get her PhD in February, and she's working on intermediate level circuit models for aperture diffraction, and she came across my work. Sent me an email, asked me a few questions. I was able to answer them, and then she sent these back to me. So she did all these computer simulations of more complex cavities and used some very fancy software to figure out, if I have a wave in the cavity, how much is going to get out, or vice versa, if I have a wave going towards the cavity, how much is going to get in. So we've got this cavity, and we've got this aperture, and she's actually looking at shorter wavelengths than I will be talking about later. But my solution that she incorporated my aperture impedances into the impedance of the modes is in blue, and their very fancy computer software is this thing here. Now, as she notes in the paper, it takes hours for this computer model to generate these results. Whereas with my aperture solution, I mean, it takes more time to write it up in Excel or something like that than it takes to do the calculations. You hit return once you're done, and you've got results. So that was for a circle. Previous diffraction descriptions that would work with things like that would only work with simple shapes like a circle or a rectangle, I think. I don't think it scaled to ellipses, but my model actually scales, I think, to any shape. So that's one of the things she wanted to try. So she modeled an ellipse. That's the orange, and then applied my aperture impedance assuming an ellipse, and that's in blue. And now we're really getting to the part where there's very little difference between the super fancy computer model and my kind of just circuit impedance. So this is great. This is just really new to me. So I'm very happy to have like independent evidence, supporting evidence. And then she looked at other things like, what if you move the aperture down to the side and you look again at a different point, and there's a lot of complicated stuff going on down here, but my simple model seems to reproduce almost all of it. Obviously, there are some areas where it gets away a little bit, like there's little deviations here or here, but now we're starting to get higher up in frequency. And then this final solution, she modeled, 2, 4, 7 apertures together. Now, my aperture diffraction solution doesn't account for any interactions between apertures. You just take 7 of them together, you get an individual impedance for each of them, then you just add them together. So now you just get like one quasi-effective aperture that's supposed to be like the rest. And again, it still does a really good job. I mean, the core structures are definitely represented. Things start to get away a little bit. The peaks aren't as high, the troughs aren't quite as low. But again, using my simple diffraction solution, it only takes seconds to come up with this versus, many, many hours for the model. So I'm very excited by this. So hopefully this suggests to you that this aperture impedance solution is actually pretty good. So now I'm going to start to switch to space science a little bit. So I'm going to start with hopefully a leading picture of the Aurora. So the general idea, very simply, is that here in the polar cap, right, is different than outside the polar cap. So I'm going to actually say inside the polar cap is an aperture. It's an effective aperture in the ionosphere. You've got low horizontal conductivities in here, and then outside the polar cap you get higher conductivities, right? So I'm just showing the Aurora here, even though that's not directly related, just to emphasize, right, you just visually see there's a difference in how kind of the system behaves based on which magnetic field lines you're at, right? I know there's all kinds of reasons for that, but that's the general idea. So here's my official model. So we've got the Earth, cartoonishly large away, we've got the ionosphere, so right, this is not to scale. And then here at the polar cap, I'm going to call this an aperture. So kind of the way I'm thinking is in the polar cap, the magnetic fields are vertical, right? So the only way you can get horizontal currents is through the Hall and Pedersen conductivity, which is not very large compared to the direct conductivity. But once you start getting near that convection reversal boundary, then your magnetic field starts to tilt. So now once you get this tilt in here, now you can get a horizontal conductivity from the direct field aligned conductivity. And since the field aligned conductivity is like thousands of times stronger than the horizontal, it takes over very quickly. Officially, I place my boundary of the aperture at the convection reversal boundary, right? So where that high latitude convection pattern changes. So why? Now, why do I think that? I mean, I gave the boundary conditions, but where did I really come up with this? And this is a slide. This is actually where I started with this idea. I was modeling an ANSYS, and this picture came out. I wanted to look at what are the fields normal to the aperture? What are the electric fields going in and out of the aperture? This yellow boundary, this is like, I talked about that bevel. So that yellow line is when it's fully flat. And this down here is when it goes back to fully vertical. So there's that small space right in between. That's just the bevel. So on one side of the aperture, one side of the aperture, the electric fields are pointing down. On the other side of the aperture, the electric fields are pointing up. And then just outside the aperture boundary, you get the reversal in that orientation, which is the exact same thing that we get with this Birkeland current system. Of course, these are currents, so if you had an electric field and a highly conductive area, then you're going to drive a current. But we've got currents that go down on the dawn side, so this, like right here, they go across the polar cap, or in an aperture, you have an electric field that's directed from this side straight across to here, just like in the polar cap. Then once you get over here, now the electric field is pointing back up, just like this thing over here with the Birkeland current system, and you get the same reversal in those patterns outside the aperture as the potential across that aperture gets shielded, right?
When you say the electric field is pointing up,
Right.
So I'm a little bit confused about up and down. We don't.
Oh, right.
There's the magnetic field aligned
Right.
currents, and so are these electric? What's the projection that you're talking about?
So when I say up, I mean, so we're like looking down on the aperture now. So when I say up, it's
A vertical electric?
vertical, yeah. So this electric field is out of the board. That's probably a better way to say it. This one's out of the board, into the board, out of the board.
I'm just not sure where that electric field is in this system that you're talking about.
All right, so
No, I don't think a vertical electric field is occurring there.
you don't in my aperture, or here.
In this over on the right.
Right, because it's a highly conductive system. So once you have the electric field, you get a current.
Yeah.
But that's the underlying field distribution that is consistent with this current system.
With very small electric fields. I don't know if that
Right.
matters.
Right.
So.
I don't think it does, but that is a criticism I get. Okay. And then I've taken some pictures that were, I just somehow blanked on the Iridium constellation. There we go. Got the Iridium constellation with a bunch of magnetometers on there, right? It's always going over the polar cap, and they can take those measurements and then fit them to basis functions to figure out, what's the actual distribution of fields and things in the polar cap. And this is what we get. It's the same thing. So it's electric fields in and out of the page in the same distribution that I have in my aperture. It's also consistent with the classic picture of what the Birkeland current distribution is supposed to be. So when I first saw this picture, I was like, what the heck is that doing there? Actually, I use a little bit more of a choice word, but I was really surprised because I'd already taken Intro to Space Science as a graduate student. I was familiar with the Birkeland current distribution, but when this popped up with an aperture, I was like, what could this possibly be doing here? That solution has no business being here because that's all related to fancy magnetic fields and plasma and solar wind, IMF, all kinds of good stuff. But the more I thought about it, right, if these two systems have the same electric field distribution, that just clearly implies they have to have the same boundary conditions. Right? There's uniqueness for the electric field. So if two systems have the same electric field solution, there's clearly something that's similar or the same between the two. So some experimental results from aperture diffraction. This also comes from France. So what they did here is they took a very thin silver film, and then I think they used an acid or something to make a very tiny little circular hole in it. So it's about 200 nanometers across. Very small. right? And then what they did next is they shot a high-energy electron beam at it. So they shot some plasma with energy, and then they could vary the energy of that beam so they can vary the wavelength of the electrons. And when the electrons went through the aperture, they diffracted, right? And as they diffracted through, they just looked at optical emissions, and they could see that if the electric field for the electron beam was like this, then across from that you get a glow, right? So you actually get these normal electric fields here that directly stimulate the emission of photons. And then they rotated the electric field, and they still kind of see the same thing. So this is my aperture modeling at a different scale, but you can just see the strongest electric fields in this kind of regime that they're talking about are right outside the aperture, and they're the fields that are normally directed. So this electric field distribution maps to this glow that we have out here. Then what they did is they measured the actual light that was radiated through. Even though electrons went through, it caused light to be radiated. The reason why they wanted to use electrons is because they didn't want their light source to be contaminating their measurements. So you send electrons in, and then you measure light on the other side. And it's the electrons that are emitting the light or causing the aperture to produce that. The measurements are here in blue. And then I took my aperture, put in 200 nanometers and all that stuff, and that's what I get here in red. So it matches the observations, extremely well. And it also demonstrates if you shoot plasma through an aperture that it diffracts in a way that I can actually describe. Very quick, I want to show kind of a convection pattern. So on the left over here, for the people online, right? This is the Helioseismology convection model. So we just get local noons up here, local midnights down here. So you get anti-sunward flow across the polar cap. Then you hit that convection reversal boundary, the flows reverse and come back. What I'm showing over here is the equivalent convection pattern that would happen when I took the actual electric fields in the aperture. Now I could have done this at long wavelengths and you would see just the thing on the left, but we wouldn't see the convection reversal because outside my aperture is a perfect conductor, so the shielding length is almost zero, right? So we don't see any of these electric fields. So for this picture, what I did is I just decreased the wavelength until that reversal would naturally occur at a radius smaller than the aperture. So you get the anti-sunward flow here, and now you can see you start to get this convection reversal, and it's a very similar pattern to what Helioseismology sketched as the typical thing. Okay, I forgot to mention this earlier, but I said, I mentioned Hans Bethe used magnetic currents to actually describe aperture diffraction. Turns out magnetic currents follow the same form as the Hall currents. So though we don't know that magnetic monopoles exist, Hall currents do exist, right? So the very current mechanisms that Bethe used are in the polar cap. Yes?
I have a little bit trouble understanding the physical mechanism. We all know that the convection pattern is driven by magnetic connection.
Right.
Magnetic pulse, whereas in your dime, everything and all the energy coming from the polar cap, right? So I just cannot reconcile this. How exactly the energy is coming, even though you do get a similar result, but does not that mean
Right. So.
The physics is right.
Right.
It's a real physics system we have here.
Yeah, so the energy I think is from the flow of the solar wind past the Earth. Yeah. So it's the waves and stuff in there, and it's actually that electric field that it produces due to that flow across that produces this pattern. And as you say, that polar cap is all about the input flux and output flux. All I can say to that is that if you watch the solutions at the polar cap, you see that electric field is always consistent with this. Now this is for IMF southward, right? But I don't think it actually goes away with northward.
In terms of energy coupling, these are two totally different paradigms.
I don't think there is because you have
What your model shows up.
because as the solar wind flows past the Earth, there's going to be waves that propagate down the field line, and when they hit the ionosphere, that's where they deposit their energy or they reflect back. So it's the flow of the solar wind that's providing the energy and the input. Yes?
Going back to the electron diffraction experiment, what kind of energies now do these electrons have?
I don't know. I put them down in nanometers. So this is obviously much smaller than the polar cap, but what's important for diffraction, thanks for bringing this up, what's important for diffraction is the relative size of your wave compared to the opening. So If you looked at this in Ka, you would see this is that peak in the dipole. Over here is all the long wavelength stuff. So really, strictly, I should only match way down over here, but I actually do much better than them. Okay, so now some numbers. So there's the picture of my Earth model. Here's the actual circuitry. This is the actual impedances that I use. And I found I had to modify the model a little bit, and that's because the Earth's surface is really close compared to the polar cap compared to its size. So the Earth is really kind of in the whole volume that this aperture would form its dipole. So I actually found through modeling that it changes the aperture impedance, and it actually leads to, it breaks the degeneracy between the magnetic and the electric dipoles. So I actually end up getting two different couplings here. So I just want to start out with some quick results. So I've got the blue, solid, and dash, so those magnetic, the electric and the magnetic dipoles. And these black measurements here were published by Stoneback. They are fast measurements taken during a substorm. So this is actual measurements right from a satellite, looking at how much power is coming in. I think he was like way kind of up here. How much power is coming in on the field lines, and then it goes past the satellite down in the ionosphere, and then you check again how much power is coming back. So you can actually produce the frequency spectrum of the transmitted power into the ionosphere. And you can see I follow it actually very well. So I'm going to talk about why there's why it only matches one of the modes. So here we go. That's that same picture again. Stoneback also published what is the wave speed of those waves that one going through. So I produced the wave speed calculations that I have for my model. Interestingly enough, you see this solid curve here matches the power very well. The solid curve down here does not match the velocities very well. So this actually demonstrates an issue with the results presented by Stoneback. I'm not saying he did a bad job, but if you assume there's only one mechanism going on in the upper ionosphere, the polar cap, those measurements don't make sense. Okay, because these two plots on the left, they're related. They're explicitly related. So if you start seeing a lot of variation in this power, you need to have a corresponding variation here in the wave impedance of the mode, and that's just not observed. There we go. Now you can see my dash one matches very well. There we go. So there's extra boundary conditions on here. So this mode, it turns out for waves from space, the power can come in, but if the system tries to radiate as a dipole, it's just not effective. It's just not effective. So in this case, power will go in, but you won't get any re-radiated waves to actually see the impedance of that mode. So that's why down here you don't see that in any waves, because it's like waves come in, waves don't come back out. On this other mode over here, this is the magnetic mode. It was not excited nearly as much. This is a substorm, so there's all kinds of currents and normally directed fields at the aperture. So the primary coupling is through the electric mode. But in the magnetic mode, you can radiate power. So whatever power is there would come back out, and thus you would actually observe it in the waves. So that explains this peak over here. Now you may remember at the beginning I said the impedance of the aperture only depends on the region you radiate into. So waves from space to the Earth behave differently than if we had a wave down here created below the ionosphere traveling up. And that actually, when you do that, the resonance gets lowered and is right down here. And that's this mode right here. The transmitted power from Earth to space is right around 0.1 hertz or so. And it turns out there's actually a slight difference between these two modes of about, 0.01 hertz, which is consistent with the beat frequency that's normally seen on structured pulsations. So this is actually how I calculated the transmitted power for all these things. You got the impedance of your wave coming in, region 1, and the impedance of region 2, effectively. It's the region of the polar cap ionosphere and the alpha wave down there. So it's just impedance 1, impedance 2, what's the power transfer network theory, straight from boundary conditions. And here's how I actually calculate the alpha velocity. It's just the impedance of the mode divided by mu. All right, so I mentioned structured and unstructured pulsations are these waves, PC waves. And we can see that there's structured pulsations that average around 0.75 hertz and unstructured pulsations that occur around 0.4. So if you look at these, this is right around 0.4. This is actually right around 0.7. So this looks like a minimum in transmitted power, but that actually produces a maximum in the field observed in the ionosphere. So you get the peak electric and magnetic fields here. So if you're looking in the near field, you're going to see these things more than anything else. And one of the modes can actually transmit power. So that mode will transmit power into the Earth, which will reflect back. engaging this mode, which will produce the beat frequency that's commonly associated with these structured pulsations, whereas the coupling with the other mode, the unstructured, doesn't engage that. And there's a latitudinal difference between these modes that's consistent with more of a electric coupling at the higher latitudes and the one of those. Yeah. All right. So as I found a lot of what I think is good evidence for the Earth. So I said, well, why don't I check this out for other bodies? So I tried to use some of my previous research on the sun. I said, okay, let's look at a typical picture of the sun, and I'm claiming that in the Earth's ionosphere, the polar cap, it's like a hole, right? But the solar scientists have already been very kind, and they already call something here a coronal hole. So basically, what I'm going to do is I'm just going to do the same thing I did for the Earth, but instead of just saying this is a coronal hole, I'm saying that's what it is. It's a coronal hole, and I'm going to give this an aperture impedance. And when I looked at all the reviews, the review literature and my studies of the sun, I found out that the chromosphere is very close to the ionosphere, right? It's a mostly neutral, but it's got some ionized gas in there, so you get Pedersen and Hall conductivities. Actually, one of the review articles I read went so far as to say the chromosphere is exactly like the ionosphere, which I thought was great, especially for this topic here. So I just did all the stuff I did for the Earth, I'm going to do for the sun. So using that review paper, I took out some average wave speeds. So this was, probably around 2005 or something, but for the corona, almost get 3 kilometers a second. And the chromosphere, we're looking at about 125 kilometers a second, and the photosphere, we're looking at 3 kilometers a second. So I put an aperture in the chromosphere, the size of the coronal hole, and then I built my model, so you get the standard wave impedance of the chromosphere based off this 125 kilometers a second. I added my polar aperture impedance. And then on the other side, you just get the coronal impedance. And here we go. And then if I calculate transmitted power from chromosphere to corona, you can see I get a peak here on one of these modes that's pretty much right on 5 minutes. So this should be another good slide coming up here. So I went to Wikipedia, said, I looked up helioseismology. I got an older plot here from Gulf of what are the dominant oscillations on the sun. Here we go. I've got my model down here, so I just dragged this plot over to this one. I took my 1 hertz, lined it up on 1 hertz. I took my 10 hertz, I lined it up on 10 hertz, and then this is a fractional power, so then I just adjusted the vertical scale until things look good to me. And here you go. I mean, right on top of each other, not only just right on, look at this thing over here. The shape. I mean, it's like right on. So I think this is actually a solution for the coronal heating problem. That you don't actually need anything crazy. The standard description, as I understand it, is the chromosphere had an impedance of blah. The corona had an impedance that was different than that. So when you had a wave in the chromosphere that tried to hit into the corona, it just gets reflected off, just like using standard network theory. But when I add the impedance of the aperture to the chromosphere, the impedance just matches. So the wave is just naturally able to go through. Okay, so I said, that's really cool. Don't need to do that. Well, what about sunspots? They look like holes too, don't they? Yeah, they sure do. So I said, well, let me apply my model to the sunspot. So here it is right down here. Where'd my pointer go? All right, so I got wave impedance of the photosphere. I used the 3 kilometers a second. I added my aperture impedance. Now for the second half, now it's the impedance of the chromosphere. That's the second, region 2. And then these are the 2 things that I get. So this is the transmitted power, and you can see there's a peak here right around 3 minutes, which my understanding that you get a peak of 3-minute waves in the umbra of a sunspot. Here's what the wave speeds look like. And after some thought, I was like, I could probably do an estimate of the temperature. So I said the power, the power radiated by a black body is some constant times t to the 4th. And then just using those typical impedances between the photosphere and chromosphere, I got that 90% of a wave is going to reflect off that boundary. So I said, what if I take all that reflected wave and just assume all of that gets absorbed right into temperature? Then I can divide by this thing, and then I can figure out what the temperature of the sunspot would be. So here's the equation. It's actually written slightly wrong, and I couldn't update it. I don't have math type on here, I guess. So the real equation here is T is the reflected power, which you can get off of here, divided by 0.9, which is that photosphere-chromosphere thing. Parentheses to the 4th root, and then times the temperature of the photosphere. And then if I put in the values here, 0.1, so this is about 85% gets transmitted, so 15% gets reflected. I put in 0.15 divided by 0.9, 4th root, blah, blah, blah. The temperature I get is 3,700 K, which, as far as I can tell, that's like right around exactly where a number should be. So then I went to the penumbra, and I said, okay, what if I do the penumbra? So the difference between the umbra model and the penumbra model is in the umbra I just changed the impedance. So the umbra, I use more of a, that should have been corona over here. The wave speeds are a little different. So, in the sunspot, the fields go way out. In the penumbra, they're more close. So I used the wave impedance that was consistent for that. And then when you do that, I get, where's my slide? You can see I get a peak near 7 minutes. And to my understanding, that is where the peak and penumbral waves are. And then I've got a couple slides here that's talking about the structure of a sunspot. So mostly the magnetic field is vertical, poking out of the sun, but you get some sidewards components. So I just applied my aperture model. What if I had magnetic fields that look like this in my aperture? Oh, just like this. Well, on the back side, I'd get this distribution, and then outside the sunspot, I'd get this. And if you add this into this model, you end up actually with this picture where some of the fields are up and some are down. And it actually maps you. Some of these are light like they're on the outside. Some of these are dark like they're associated with the sunspot. And it actually, all those things kind of work out. So if I use this peak here, about 70-something% is transmitted, then I get that. No, I'm sorry. So if I use the peak over here at 5 minutes, that's right. If I use the peak over here at 5 minutes, I use that reflected power in my equation, then I get the penumbra temperature is about 5,300 Kelvin. If I use this upper peak here where more gets transmitted, less is reflected, then you're looking at 4,500 Kelvin. Okay, so if something works for the Earth and something works for the Sun, then I said, well, what about black holes, right? A black hole is just a failed star or an end of life. And I remember there's an article that came out in the New York Times a long time ago. It was talking about one of the largest structures, about the Perseus cluster. Right? It's got super massive black hole in the middle. And what was surprising here is these astronomers found evidence that it had been producing a wave at a constant frequency for a very, very, very long time. And it didn't really kind of make sense. Why would something be making a wave at a constant frequency for a very, very long time? Well, if the black hole is like a Helmholtz resonator, there's not really a lot of reason for it to change. This magnetic field is already huge and probably percentage-wise isn't going to change over time. I even did more detailed investigations, and around a black hole you get like an ionospheric layer too. So you get Hall and Pedersen currents that flow around. So it's possible that this Perseus cluster is actually showing some evidence of the same thing by having this very long-term constant frequency system. All right, so that's my space science. I guess that's technically my 50 minutes. I'm out of time. If I can go over a little bit, I can spend a few minutes talking about my light guitar. I don't hear any no's, so I'll go ahead and say yes. So here's a picture of my light guitar. You can see I tried to make it just like an acoustic instrument, except I made it out of metal. So this is all as a grad student. I couldn't afford gold plating, surprisingly, right? So I had to try to do the next best thing. So I made this out of pure aluminum. So aluminum oxidizes very readily, but then once it does that, it stops, right? So you get like a monoatomic layer of oxygen, but the aluminum itself is still highly conductive. Only problem is it's not very easy to weld. All right, and then here's kind of how I play it. So this is an electromagnetic anechoic chamber. This is a vector network analyzer, so it sends waves down this coax. And when the waves hit the guitar, some goes into the guitar, some reflects back based on the impedance of the cable versus the impedance of the guitar. And the VNA measures that reflected wave. So out of that, you can actually get what the impedance is. From that, I can do things like load it on the computer and put it into programs like GarageBand. So just real quick, acousticians also describe guitars using circuits. Here we go. Here's an example. So this is a paper from the mid-70s, I think. I went one too far. Oh, you're giving away my stuff. All right, so here we go. So this is about 1976, I think. So they wanted to figure out about the Helmholtz Resonator. So this curve down here is the guitar with the sound hole open. And you see you get a peak here and a peak here. This is a body resonance. This is related to the Helmholtz resonance. And then they covered that hole up, did the same experiment. Now that peak's not there anymore. So I said, I want to do the same thing. So I did take some measurements. I got measurements of the body itself. And then it turns out I actually ran out of time before I could do the full-on aperture experiments. But so this green curve here, this is the impedance of my E&M guitar, just straight out. This blue curve is, I said, hey, I should take that model I developed for the Earth, since it worked pretty well, and stick it in here. And this is what it gives me. This is a resonance right here, which is right around 100 megahertz. And as for comparison, here's the acoustic circuit. Its Helmholtz resonance right around 100 hertz, which is about a factor of 1,000,000 apart, which is about what I would expect. It's actually, you'd expect a factor of about 863,000 based on the ratio wave speeds, but I like to call that 1,000,000. All right, and then over here, I'm just showing an extended plot of what my E&M guitar circuit looks like. Normally for an acoustic guitar, right around 1 to 2 kilohertz or so, everything would go down to 0, but that E&M guitar is really just starting to get started. So, and it's just going to keep going. So how do you actually listen to something like this? Well, I tried to, I followed something that's already a product that was already out there. I'm missing something over here. Okay, and I don't know where this came from. But anyway, so there's this device. This is old now, but this is called the Pod. This came out, I think, early 2000s. So what this company in Line 6 did is they went out and collected a bunch of really classic amplifiers and guitars and things that were really expensive and people really liked, but most people couldn't afford or even find. So they took a bunch of measurements of these things and then they loaded it onto this pod device. So once you get your basic electric guitar at home, you plug it into the pod and then you change the knobs on the pod to select, I want the Jimi Hendrix version guitar out of the very fancy Marshall stack or whatever. And then they use those real world measurements to modify the input sound. So now your guitar kind of sounds like the Jimi Hendrix guitar. Doesn't make you play like Jimmy though, but here you go. So I said, I can do the same thing. So I have the frequency response to the E&M guitar. I can, that's equivalent to having the impulse response, which is actually everything you need about the system. So I wrote this plugin that runs in Apple GarageBand. So on one side, you plug in your guitar, whatever music into your computer, you run it through, it goes through my plugin, and then I convolve the input music with the impulse response of my guitar, which makes it sound exactly like it's coming from the guitar. But it's not light waves anymore, it's just sound waves. So I also convert the frequency down from 20 megahertz and 20 gigahertz down to 20 hertz to 20 kilohertz. So that's the overall plan. So I used part of my startup money at UTD to build the studio. This used to be a storage closet. So this is the one I did for my dissertation. This guitar over here is the first guitar that started it all. So you can't see it, but it's got an S-band waveguide on the bottom, and then I built just like for the same dimensions, I built this electric guitar here, and I wanted to look at the shape of these pickup cavities because I was building my own guitar at home, and I wanted to see if this one was good. So the plan here is to, I'm getting undergraduate and other students to come in here, get them excited about music and things like that, and then I can use that as a mechanism to move into space. So every time I go and talk to physics students now at UTD, I collect at least like 3 students that want to come work in my lab. So that's going pretty well. UTD is building a new physics building, and they've actually asked me to supply a sound file for this art installation thing that they're doing. So supposedly I'm going to work on that this month, even though I've got travel next week and then the week after. And the week after. So that's what I'm going to be hopefully working on when I'm not working on Icon and Cosmic. And then I just thought it'd be fun to show you a picture of me when I was in grad school. So this is me on my India trip out at one of the Gong Network sites. And so I guess thanks to the NSF for starting some of this stuff off. And thank you to all of you for showing up today and giving me the chance to share some of my less typical research. All right, thank you.
Questions?
Yeah, could you go back to slide 18? I'm not sure that this is going to draw out the issue, but if I understand your cavity model, the boundary conditions are essentially homogeneous, uniform. We know that the ionospheric conductivity is anything but uniform. Even in the polar cap, you have the EUV ionization, which creates a very high conductivity region on the day side, depends on season and so on, relative to night side. How does that enter into your calculation, or how would it modify the results? And might that have something to do with the differences that Stoneback sees relative to your results?
Well, so if you're talking waves from space to the Earth, I don't think that would matter because the aperture impedance depends on the region it radiates into. So for that, we're talking about the space between the ionosphere and the Earth, which is, just atmosphere.
But surely the boundary conditions at the bottom of the cavity, I mean, in the impedance model that you showed us, you had a perfectly transmitting or absorbing boundary condition.
When it radiated in there, but that space there.
Got to the cavity walls and so on, and then it was totally absorbed at that point.
Right.
Here, I don't think that happens.
Right. So yeah. So if waves come in and they'll come back, then it'll be from the Earth to space, and in there it would matter. From the math that I have, you would end up taking an average over the whole polar cap to get kind of what you're talking about. But it's not just the layer; it's also like the volume. So you're more interested in what like the ionosphere above is looking at than right at that lowest layer.
And I'll leave you just with another thought. I don't know if this has come up in your research into the application to the polar region, but the Alfvén velocity is very non-uniform.
That's right.
You probably know.
Mm-hmm.
And there is this so-called ionospheric Alfvén resonator.
That's right.
Which traps a lot of power
Mm-hmm.
and absorbs a lot of power
Mm-hmm.
at harmonics of the resonator.
Mm-hmm.
I'm also curious how that might affect.
I actually found that my model is very consistent with all those frequencies. So I had it in my manuscript, but that turned out to be one of the reasons that this was rejected for the first time was because one of the editors is like, you use the word ionospheric Alfvén resonator, and that's already has accepted solutions, so you're out.
Can't reuse that.
Yeah.
Call it something else.
Yeah, so I've taken that all out. Unfortunately, I still haven't been able to get any of this published. So I have a really high quality manuscript, I think, but so I'm still working on it, 10 years and counting. So if anybody wants to be a reviewer, not asking for a free ride or anything, but.
Any other questions? Okay, then thanks.
All right,
Russel,
thank you.
Again.